Awesome. We're already a few minutes late, so I'm gonna just pass it to Tyler if you want to kick off. You're
Cool.
muted,
Yeah,
by the
thanks,
way.
guys.
Yeah.
Oh, nice slide.
Um,
Slides.
yeah, I was messing with all the
Man,
Google
Tyler
Slides
is
templates.
really like spoiling the market.
I don't know. I think I did way too much prep for the last presentation. So this one's definitely going to be a little bit more winging it. I'm going to switch over to Zoder in a minute, but I wanted to do a title slide. Cool. Yeah. So currently doing a master's at Georgia Tech, focusing on ML. Have another semester and a half left. But yeah. And then today we're doing HRM. This is a cool paper. Gonna try to go through the paper for a chunk of it, but I also want to talk about some of the like the arc analysis stuff. So I'll post a link to their write-up in the chat. Maybe we can dive into some of that too. But let me actually just switch back to Zoho because I think it's a better way to do it. Um, so yeah, I mean the headline with this paper that like made a big splash was that it did pretty well on Arc AGI 1 with like a pretty small model. Um, and then there's certain types of problems they highlight, Sudoku and Maze, where it like dramatically outperforms sort of the leading reasoning models. Um, and they attribute a lot of this to this architecture
Tyler,
that they proposed.
are you trying to get your slides on the screen? Or because we're not seeing it, or at least I'm not seeing it.
Uh,
Okay,
okay,
it's
is it
back up.
sharing now?
Yep. Now it's sharing.
Okay,
Thank you.
okay. Yeah, was it sharing before? Yes. Cool. Okay, cool. So yeah, 27 million parameters. That was a big splash. They cite a lot of this as being from their like novel architecture of this like two levels of recurrence. They have like a high level and and a low level. And they spent a chunk of the paper talking about like this correspondence to neuroscience and some of like mechanisms in the brain and mouse brain stuff. I don't know if there's actually that much evidence to support that, so I'm not going to focus on that too much. But I guess starting talking about um, the the types of challenges that they face. I guess one of the things that they cite is the challenge of um, a fixed amount of compute that's used for chain of thought. So every time you do like an inference pass and generate a new token in autoaggressive model, you're going through like the same number of blocks, and your attention mechanism can help decide which of the previous tokens are most important for upcoming calculation. But for each forward pass, like you still have, you know, 80 layers or whatever. Um, Whereas with their model, they have a little bit more ability to change the amount of computation that's performed um, per problem. We'll dig into that a little bit more. Um, they don't really discuss it, but they talk about this being kind of latent reasoning versus always having to like generate a next token for chain of thought. So you kind of have like this back and forth between like generating a token and then re-embedding it. And of course, some of it can stay in your cache for previous tokens. But with latent reasoning, the distinction they draw out is that they are able to keep stuff in their hidden state space, and they pass it recurrently to the next pass. Um, they call this like the carry. Also they said the thing. Um, do do do. So yeah, that so fundamentally constrained by the model's computational depth. Um, the two big pieces they draw out in the architecture are this the high level module, which they cite as being for abstract and deliberate reasoning, and the low level module for fast detailed computations.
Did Tyler drop out? Uh-oh.
I think he froze. He is
You
in
don't
fact frozen.
we don't get, well, no audio as well, so okay, we'll wait. Oh, and we haven't shared the meeting yet? Okay, let me copy the invite link. Oh, Tyler dropped out for a bit. Tyler's back.
He's back.
Yes.
He's frozen again.
Hmm.
Okay, sorry
Okay,
about that.
Tyler is definitely back now.
Yeah,
Okay.
this one's pretty good. It's gonna stick. Okay, so we were just talking about the two levels that this is the
Do you want
hierarchy
to
that
share
they,
your screen again?
yes, sorry. It's like only ever happens on these calls. Cool. So the hierarchy they specify is this high level module and the low level module. And just gonna skip ahead a little bit to the diagram. This is on page 6, figure 4. They have sort of these L modules, the low level modules, which are able to iterate. They call them n times, and then for each n iteration, there's an each module step, and then they can repeat the L modules and then each module. So this is like the inner architecture. There's like an outer one where they have even more adaptive compute, but this is sort of the hierarchy that they talk about. Do, do, do. Okay. And then they compare it to like a normal transformer. And this is the comparison of like the amount of computation that's able to be done. I think from like an abstract level, it sort of makes sense. Like that if you think about like how to solve a Sudoku, if you're doing like this is like a LeetCode problem, you would solve it using backtracking. So if we're trying to figure out like what the value in the top left is, then you would try like each potential option. And then if that doesn't work, then you kind of go backwards. And so to exponentiate the whole search space, like the whole search tree for solving Sudokus, like something like 9 times 9 to the 9th, or like 9 to the 81st. There's like a lot of possibilities to potentially solve for. And if we're just doing like a normal compute budget with like standard passes, then those all have to be specified in tokens. Like the model has to like spell out in JSON or CSV or something like what it thinks the state space of the Sudoku is before trying to plan or backtrack, which is pretty token intensive. And so doing the latent space reasoning, they attribute to being like one of the ways it's able to work around that. Okay. Any questions so far before we get into the architecture? Cool.
Was it only doing gradient optimization on the step through the forward pass where the end token was output. Was I reading that right?
Yeah, we're gonna get into that right now.
Yeah.
Yeah.
So yeah, I mean, I think just to follow on that, they have, so if we have our like supervised task here at the bottom, for each training step, this is kind of like pseudocode. They call the HRM with a previous latent space, and the input value. And then from that, they get a prediction and an updated latent value, which then gets passed to the next iteration. And then they use like this pass to then do a gradient update, which we can see the model up top. So yeah, on the forward pass, they generate like the low level latents, and then for each T steps, they generate the high level latents. Yeah, and then that gets updated when we do a training step. And this uses a variant of Atom as the optimizer.
Makes sense to me. What's the intuition they have when they say that they detach the latent space? Is it that in default standard RNNs, we actually backprop on that latent space embedding? Because it seems like they're still backpropagating on the model parameters itself. So I don't
think
quite.
it's I think it's potentially like as a workaround for vanishing gradients, which I know is like commonly a problem when training like regular.
So instead of vanishing gradients, they
RNNs.
just drop it, so that we don't have to backprop on that.
Yeah, I'm not actually sure.
Yeah, this is the one thing that I'm not very certain of. And
Yeah.
I'm also not very familiar with RNNs, at least not this aspect of it.
Yeah, I know. I wish we had Eugene Chia on.
Yeah, he would be perfect for this.
Totally. But yeah, they pass in like this is in the diagram too. That there's like the previous latents from the last pass. They also make a point of using there's some recent other work that's come out on deep equilibrium models, which I didn't really dig too far into. I sort of skimmed that paper, but I think that's sort of their rationale for specifying it like this, where they spell out the gradient path. So we have like our loss function and then our output head that generated the loss function, and then that comes from the final state of our high level module, the final state of the low level model, and then back to the embedding. So if you're thinking about like the computation graph flowing backwards, this is how they lay it out, and so they don't have to unroll the whole thing for like all of the recursive steps. And then sort of the proof that they show is like this section where they do like an approximate values for the different partial derivatives for calculating the gradients. Okay, yeah, so this is all the optimizer stuff. the next big chunk that I thought was pretty interesting is this adaptive computational time, which acts kind of like outside of the hierarchical reasoning model.
One thing before that, Tyler, I had a question. Just
Sure.
before adaptive computation time, yes, the last sentence that you highlighted in blue. This provides more frequent feedback to the H module. Why? Why the fact that we only do backprop on the last time step? Why does it provide more frequent feedback to the H module? Do you know the intuition behind that?
I don't. I mean, I think to me it would make, like, it seems, my intuition is it would be the opposite, that it provides more feedback to the L module.
Yeah, I
because
was
that's
kind
the
of
one
stuck
that's
on
like,
that as well. Yeah.
yeah, it gets like looped less.
It's okay. I mean, I wonder if anyone knows, and if you do, you can feel free to chime in. If not, it's also fine. Something to dig into maybe a bit later. Okay, we can move on to adaptive computation then.
Okay. I guess, yeah, one call out here is, before we get into the adaptive stuff, is they do call out this this thing called a segment, which is like one of the loops through the low levels and then the high level. So for, yeah, the adaptive computational time, they have like a separate learning objective that they do through Q learning to determine either to halt or to continue. So this is like the state space is just these two states, either halt or continue. And then the Q values are to predict whether we should halt or continue. And if it's the two, yeah, and then correspondingly, there's two actions, halt and continue. And if we're halting, so this is we use ym if this is true, and then we ignore it if it's false. And then if it's, so if that, then that's when we halt. And then for the continue step, then we take the max of these two actions. And this okay, so yeah, so there's another binary constant should be lost between the Q value and our reward from getting this correct. And then this ends up getting combined with actually, maybe they don't specify it. Okay, so yeah, they combine the two losses, but I don't think they've got the equation for it. I've got that in notes. So the whole goal with this is like trying to determine how long this should continue for. And they're they did some evaluations to determine like how effective this was, and they showed that by varying the adaptive compute time and adding this ACT mechanism, that they were able to improve the results compared to like a fixed compute budget. And that this also worked to at inference time. So this was in training, and then in inference time, that the performance or the amount of compute that was used was able to be scaled dynamically using the Q objective. Okay. So with this, both the H and the L modules use normal transformer blocks with rotary embedding, GLUs, RMS norm, and no bias term. So pretty standard modern architectures. And then let's see again. Yeah, I did well on the arc puzzles. One of the things that they don't really talk about very much in the paper, which I think deserves more time. So I'm going to spend a little bit more time on it. Let's see if I've got it. Okay. Okay, cool. Yeah, that was the next section. Cool. So yeah, they call out some of the backtracking that we mentioned before. And they cite that like the normal Sudoku problems that like most reasoning LLMs, they classified in terms of the number of backtrackings required to solve the puzzle. And that the data set they created is significantly harder than like the standard ones that are tested on models and requires a significant more number of backtracks. Yeah, the standard ones are 0.45 backtracks per puzzle. Okay, yeah, here's the part. So their procedure for test time is pretty interesting. So for each test input in the evaluation set, they follow these steps. First, they generate and solve 1,000 augmented variants, and for each apply an inverse augmentation to transform and obtain a prediction. So for that first piece, they do like a bunch of rotations and like, you know, transform on the like your input matrix. They change the colors for some of the arc problems and generate like 1,000 different variants. And then they try to solve those. And these augmentations, they create in an invertible way. And they, after solving it, they invert the solution back to the original. So they all can kind of be normalized. And then of those 1,000 solved samples, they choose the 2 most popular predictions for the final outputs. So for like a single Sudoku puzzle, they try to solve it like 1,000 different ways, each one with varying compute. And then they map everything back and then do like a best of 2 voting to determine which one they should use as their final answer.
Yeah, this stood out to me too. Is this standard for how AGI inference is done? Would you
I
know?
don't think so. There's another paper that I didn't follow up on yet, but I think made a little bit of a splash a few months ago. It's like solving ARC AGI with no pre-training or something like that. And in the ARC analysis blog post, they talk about that paper and how this kind of like relates to that a little bit.
I see.
But yeah, I thought this was like kind of crazy that they it's not just like their model architecture and all of that. Like they solve like 1,000 different variants and then try to map it back to obtain the prediction. All of this is just like it worked. And they spend a little bit of time trying to understand like or interpret what the model's doing during inference. So
It's 12:30.
starting at the top here, like at the first time step I2, there's like a bunch of potential paths for this maze. And we can see at like the next iteration, there's still a couple different paths, but it's starting to get cleaned up a little bit. And then as it progresses, it's starting to converge a little bit more on an optimal path, but it's still like disconnected. And then finally at time step I equals 6, then it was able to create like a final solution. And so this is, I think these refer to like the segments that we talked about before, where it's like a series of low-level passes and then high-level pass. And for the number of time steps, I think that's determined by like the Q learning halting values. So it doesn't just like continue on this without like large changes. And then similarly for Sudoku, red is bold cells represent the initial givens. Red highlights cells violating Sudoku constraints, the false ones. And gray shading indicates changes from the previous step. So that's the gray shading. So we can see like where the values change, and then the lighter gray ones, I guess, start to converge to like a solution. And then finally it like starts to settle. And then does like a similar process for the these two arc puzzles, which is pretty interesting. They make a big point again about this like brain correspondence, which is like, it's fun to think about. I think, you know, taking neural inspiration is like pretty interesting. I don't know that much about neuroscience, so it's hard to validate like if this actually matters or not. But they found in the course of training that that the high level layers or high level module learned a representation that was different than the representation of the low level module. And they evaluate it using this thing called the participation ratio, which is I've almost been thinking about it as like it's kind of like a PCA. It's like how many principal components are in the different layers. So these are lambda is the eigenvalues of the covariance matrix of the different neural trajectories. So that's kind of like how many different things does this try to do? And this tries to create like a single number from the number of eigenvalues. And so a higher number corresponds to something that's like has more principal components, and a lower number has fewer principal components, reflecting a more compact lower dimensional structure. So through the course of training, actually, I think this is, they do some experiments to vary the number of trajectories that are generated. I think there's different types of problems. And as the types of problems are increased, that the complexity of the high level module increases faster than the complexity of the low level module. And then if they just like train on noise, then they pretty much stay the same and there's not a meaningful difference. So something about like their model architecture created this emergent property where the high level stores more complex features than the low level. And then they make a big deal of like the ratio between the two at 100 trajectories is very similar to the ratio of some of the neural structures that were found through fMRI on mice brains. That doesn't really mean that much to me, but they spend a chunk of the paper talking about it. And they also talk about like some pitfalls with this link, and that like really more research is required to kind of dig into that more. I think those are the main things I had from the paper itself. Are there questions as we dig into this? Or other stuff that people noticed as they read through it? Sorry, I
I
have
think
one in chat.
Philip has a question. Do you think for ArcAGI, it lacks operations like symmetric flip and autoregressive pixel painting? It's not what a humans would actually do, or is that not a major limitation? I don't know if Philip, you want to come on camera or just speak up to just add more context.
Yeah. I was digging
It's not
into
clear.
the code of this a little bit more. Oh, sorry, go ahead.
I mean, in ArcAGI, there are tasks that require like human perspective. For example, flipping, working on shapes, something like this, and not actually painting the pixels itself. Do you think it's like major limitation? Because the score of this model is not like really high on the benchmark on the AGI. What do you think? It's like, is this a limitation or are there other major limitations?
I mean, I think potentially the arc analysis digs into that a little bit, and they just to back up a little bit, like these are the different operations that they outline. They call them like dihedral transformations. I think that's like a so the different rotations, different flips, and the different reflections. And each one of these is like an invertible operation. For the ARC data set, yeah, it looks like they do all of them. And then in the analysis itself, this is jumping ahead a little bit, but they cite like the pre-training task augmentation as being critical. And they did some experiments where they limit the amount of augmentation that's done, and they found that it had a dramatic impact on performance.
Okay, thanks. So they use this methods.
Yes, yeah. So let's just do this one. Okay, so that's the model architecture. So there's that blog post I was just looking at, the black screen, and then they created a set of slides. And I stole most of the slides, so I'm just going to go through them kind of verbatim because it's a nicer way to condense the information. So ARC was pretty like interested in this model architecture because it did like pretty well with such a small model. And so they went through and were able to largely reproduce many of the performance, or a lot of the performance that the paper originally cited, and they were trying to dig into why. So the 5 things that they looked at were the architecture itself, the inner refinement loop. So that's the relation between the high level and low level, the outer refinement loop, that's the ACT part, the data augmentation, and then puzzle embeddings, which we didn't really discuss, but we can talk about it in the context of going through these individual steps. The paper achieved 41% pass at 2 on the public AGI data, And then they were able to reproduce 32% on ArcV1 on their semi-private holdout set. For ArcV2, which is the one that was released this year, and is supposed to be significantly harder than ArcV1. The paper cited 4%, and then they got 2% on the semi-private. And then this background is the performance, the score percentage per task of HRM. So it did, similarly to Claude Opus 4. One thing to note is that the cost per task was reasonably high for this, because it had to do all of like the 1,000 solutions for each individual problem. And so they had a runtime of something like 12 hours to solve the 100 problems in the semi-private set. And then so if you prorate that per problem, then it was like $1.48 or something, versus like a pre-trained model doesn't incur the same costs. The costs are in generating the chain of thought and all of those tokens. I think this is out of order. Okay, yeah. So the first thing they looked at was like, does a model architecture matter? And they subbed in a normal transformer with the same number of parameters as the HRM, and then trained it with the same objectives, and found fairly similar performance. So blue is HRM, orange is transformer. And as the number of refinement loops increase, that there's a slight edge to the HRM, but it wasn't like the chief like leading force in the performance gain of this model. The next thing they looked at was this hierarchical inner loop. So this is, the correspondence between the number of H and L cycles. If you have a lot more L cycles, does that matter? If you have fewer L cycles, so more frequent H cycles, does that matter? And they did a little bit of experience. They said that they speak in costly really quickly, because it's like a sort of an exponential increase as you increase the number of these inner loops, like everything gets bigger quickly. But even with just one loop of each, that it achieved like a similar level of performance to the 2L to 2H correspondence that were the config parameters used for the actual model.
Hey, Tyler, quick question.
Mhm.
Adam had a question. The refinement loops chart, I think it's the previous chart. Does this imply doing the same tool use style image flip, or does it imply the segments, more segments?
I think this is keeping everything the same. So this is like 1,000 augmentation steps.
So what is a refinement loop? Is it an additional segment, or is it an additional piece of data augmentation?
I think it's another ACT step. So it does like the
Yes, yeah.
yeah, the recurrence of the low level with so 2L 1H 2L 1H, and then if it decides to go on, then it's like another refinement.
That makes sense. So it's okay, got it. Yeah, thank you.
Wait,
Yeah, good question.
Doesn't the transformer not have the HL loops though? Given that
It does
that's
not. That's correct.
They
Yeah.
add those.
Yeah. So what's
So they-
what would be the equivalent in transformer loops?
There isn't one. So this was testing to see how does their novel architecture with the H and L loops perform against like a transformer of the same size, same number of parameters.
Oh, but the x-axis shows that the transformer with 2 loops though.
Yeah, if it's
2
if
loops,
it's
8
high
loops,
loop,
16 loops.
there's something happening.
Yeah, that's a good question. I didn't dig into that. I didn't think to dig into it. Like, yeah, what is how is stuff passed to the next refinement? Like, is there some sort of latent representation that gets forwarded? I'm assuming there would have to be, but that would be a really good thing to follow up on.
Thank you, Tyler. Thank you, Adam.
Yeah. Okay. So this is digging into like sort of the same stuff.
Hello?
This outer refinement. Hey, yeah, go ahead. I just been a hot mic.
Yeah.
Okay. Yeah, does the outer refinement loop matter? So similarly, they're trying to isolate, like this is an independent variable, and they vary the number of max outer loop steps. So with like, we can see the x-axis here is 1 ACT loop, going up to 16 ACT loops, and then comparison against a fixed 18 or fixed 16 loops. And the comparison here is between training with the Q learning objective versus always training using 16 steps. Sorry, I think I said that wrong. This is, yeah, variable training with inference steps and training, yeah, always training with 16 and then variable inference steps. And they found that like with training, refinement at training makes a bigger difference than just refinement at inference. So we can see for 1 ACT step, then this training with 16 outperformed the one with variable training. Okay. And then this is starting to look at the data augmentation stuff. So again, yeah, they varied aug 10, so this orange is 10 augmentations. And then 30, 100, 200, 400, 300, 600. We can see that the data starts to peak at these higher numbers, but even at lower augmentation, a lower number of data augmentations. So if you look at the 100 augmentations, we achieve a lot of the performance of the larger problem set. And even with it like 10 samples, then it still has a decent performance. So the conclusion of their analysis on this was that it made some difference, but you don't necessarily need to do 1,000. That it likely plateaus before then. One thing we didn't really talk about in the paper and isn't really discussed that much in the paper is how they embed the inputs. So they feed, they have like a learned embedding, and then they feed in like a puzzle ID, and create like a unique hash for each puzzle ID that then gets learned during training. And this was kind of in, instead of giving like explicit instructions. So in, for a Sudoku puzzle with like if you're going to give that to Claude or something, you probably give it like a long prompt saying like, this is Sudoku, here's how you solve it. Here's some procedure for potentially solving it. Think out loud. because this isn't like a large language model with a huge amount of pre-training, they try to encode the objective of the puzzle in this puzzle embedding. And so that there's like some relationship between the type of puzzle and the task that it's trying to solve for. At least that's kind of like my understanding of how this works. But if anybody has like a better idea, we can feel free to chime in. And so given that those puzzle IDs, they then do another check on the number of augmented examples and found similar results to what we were looking at before, that like this works in the context of the problems that this was built for, so ArcGIS-1, Sudoku, and the mazes, but doesn't generalize to like other problems outside of that, and was like a challenge of this research is like it would be a challenge to extend this to like new novel problems that don't relate to kind of like the puzzle IDs that they trained it on. So it's sort of like tailor built for these problems. Cool. And that's what I got. But happy to dig back into any more of this stuff. Or if other people have thoughts or questions.
This is great. Thank you, Tyler. Do folks have questions? Yeah, I asked all my questions throughout the presentation anyway. So
Cool.
Apologies.
Abdullah
thanks,
has a
everybody.
question. Oh, go for
Yeah, thank
Abdullah
you.
have a hand raised, yeah.
Yeah, thank you. Can you hear me?
Mhm.
That's great.
Yes.
Thank you for the presentation. So it's clearly a very interesting architecture, and the efficiency of the model is really interesting. However, like chain of thought, when it came out, it allowed for a lot of work on AI safety, even though it doesn't allow for like exact like mechanistic interpretability, but it allows us to kind of introspect the model and what it's thinking about. However, with this kind of model, hierarchical reasoning model, I think this is not possible. I'm curious what you think can be done in terms of evaluating the safety of those models.
Yeah, I mean, I think at the model of this scale, it's less of a concern just because it's like it really is tailored just for these problems. There's not that much of like a safety concern for solving Sudoku. I think, if this type of architecture continue to be scaled up, then I think some of the approaches that have been pioneered in the mech-interp world would still be applicable. We can introspect on what values are activated. It still uses a transformer, so a lot of the research that's been done on that is still applicable. There's probably a different type of like circuit analysis if we're trying to dig into deciding what it is. But my guess is that like the superposition would still apply, that it's still learning some representation that we can then kind of like tweeze apart a little bit to try to better understand what it's doing. But I think the direction that they kind of outline in this paper, where they look at like what are the intermediate values at each of the iteration steps, I think is helpful for understanding like what this model is doing.
Okay.
Cool.
I think
Well,
someone was speaking earlier. Was there something like
I talked over Abdullah earlier. Sorry.
Adam, go for it.
I didn't read the paper before jumping into this, so like apologies for if it is something that's quoted obviously in the paper, that's me being lazy. But was there did they have like sort of percentage of parameter counts that were involved with the high level versus low level spaces, and like, did they vary that, and what was that like?
Yeah, I don't think they did a lot of like hyperparameter search on that. Both the high level and low level architectures have the same number of parameters. Let's see if I can pull this up. Sure what happened on that page, but also I've been using DeepWiki a lot, which I learned about from the Latent Space podcast. So shout out to that because it's actually a pretty useful tool. Do do do. Sorry, I don't have it in my hands, but it's like 768 by 4 or something. It's like not very big. Okay, yeah, that didn't get to it either, but I think that's roughly what it is.
Okay, no, Frankie has a question as well.
Yeah, go for it.
Yeah, so I think we were talking about the transformer outer loop in the comparison against the HRM outer loop. And I was thinking about it. I was wondering if they're using the same recursive feedback. That is, traditionally you just go through one iteration, right, on the transformer. So it feels like to me what they're saying, at least in the work from Andia, is that they're feeding in the output, right, of one transformer run, feeding it back to the input. But then I'm a little bit, that seems like what they're doing, but I don't want to say that because the differential here is that even in HRM, you continuously feeding back X, right? So it's not like on HR tertiary, you're still like going through X, right? Although they do have the recursive nature, you're feeding X. So somehow the transformer one, I'm not sure how they would do that, and they didn't explain very well. But I think that's what it means. Like you have X amount of refinement loops in the transformer architecture only. That is, I think that they're trying to just remove the inner loop, outer loop kind of thing, and just have like a pure transformer number of layers going through, but iteratively.
That would make sense to me. Yeah, thanks for digging into that a little bit more.
Oh, Tyler, can you do one thing? Can you stop the recording?
Yeah, absolutely.
It should be on the top right side. In case